Team15 and the language I've developed is Marshmallow. My team is Amresh, Balachandar, Ijaz, and Prashant. So I would like to go ahead and describe the language I've developed. So basically, our language was developed from C++, from the scratch without the use of any tools. Our language was motivated from Python and Java. It basically follows the imperative programming paradigm. The grammar of the language basically supports expression precedence. So basically, our language supports a lot. Basically, can support assignment, arithmetic operations, logical operations, comparison operations, assignment operations, identifiers, print statements, continuous statements, return statements, break statements, conditional statements, loop statements, and functions. Our language also supports nested functions. So basically, the grammar. So our name of our language is Marshmallow. Should contain at least one or more statements. We have the grammar basically supports expressive precedence. So letter can support basically it can have A to Z. It can be either from lowercase, uppercase. We basically have a digit, and our identifier should start with a letter or underscore, and it can have more than one or more letter or underscores, a combination of them. Our function name should be an identifier. Digit should have at least one or more digits, and we have various statements. And our block line actually follows the structure of a new line, an indentation, one or more statements along with a didn't. Our if statement structures basically an if with an expression block, zero or more elif expression blocks, or an optional else with the block. Our while statement structure is basically a while with an expression and a block. A function definition will basically have the keyword function with a function name, the parenthesis block, and the rest of the grammar can be actually is in the slide. So basically, I would like to explain the design flow. So basically, we actually have the source code passed to the Lexer, where the tokens are generated, and the tokens are then sent to the parser, where the parse tree and symbol tree is generated. Where again, the parse tree and symbol tree is sent to a bytecode generation, where we get a bytecode, which is sent to the runtime environment with the output. And the code structure of the Lexer program. So basically, the input is a vector of characters. So these are the list of the keywords that we consider, and based on each character, we push our tokens. And in this lecture, we basically check for a number of indentations and indentations, and we ensure it's balanced. And if at all you didn't more than how much you indent in a block structure, we basically throw an error, and we'll show you a sample execution of a test lecture. So this is our program that we are going to run. It contains a nested if conditions and certain Boolean logical condition where we can actually AND or perform AND or operations. When we execute, we basically get the following list of tokens. And when we run a Marshmallow program, we basically get a binary file, which is then given as an input to the Mellow, and where we basically get our output, which is given here f, which is 1, and it is here printed here. Now let's look at how my teammate will.
Hi, I'm Balachandar, and my contribution to this project is writing a parser. So the parser here is written as a recursive descent parser. What's this recursive descent parser is like each productions of a grammar is taken as a single separate procedure and is being converted into a program. Let's take a sample program, and here we see like let's go to the next slide. So if we see here, the top one is the program node, and it contains 4 child statement nodes, and the left one is expression node, and the second node is a function node, and the third one is a print node, and then the fourth one is also a print node. Here we can see what is the structure of a parse tree that we have generated, as it is like this parse tree is generated by recursively passing down. And let's see the symbol table as well. So the input to this parser is basically tokens from the Lexer, and from the parser we generate the symbol table as well as the parse tree. And symbol table, in the symbol table basically what it contains is the identifier name as well as the address. So by using the symbol table we are managing the scope as well. Let's see the structure of the symbol table as well. So this symbol table is like a doubly linked n-array tree structure. So here we have the root symbol table, and we have a child symbol table, and then this child symbol table again has two child symbol tables. And this is how what we have done here is like if we want to for example, basically, if inside a if loop, if we are going to access a identifier which has been declared outside the function uh, in the main, so what we can do is like go through the lookup. For example, here we have defined g equal to 2 in the child table 2. If this has been defined in the root symbol table, so we can like look up through the parent maps and go and get the value or the address if it is has been altered. And this has been used for semantic analysis as well. This helps to detect if you are trying to access a identifier which has not been declared, it will throw a error. And let's go to the code of the parser. And so this is the parser code. Here we have the lookup function, and we could see actually here, so these are the program statement nodes, and then we have a block node. So these block nodes are basically based on the grammar, it has been converted into code. And let's see how the program runs as well here. And so yeah, this is the program that we are going to try here. See, so basically this malloc is the compiler program that we have written, and scope test.mlw is our source code file. So once we run this command, we will generate a bytecode file that contains the intermediate bytecode. And we have to, and here the malloc is our runtime. So basically once we give the out bytecode file to it, it will execute. And here we can see the value is 7 and 3. Even though the variable which we have passed as 3 is the value which we have defined earlier, even though we access the variable again and we store it as 7, once we print it in the mangle of n function, we get the variable as 7 by based on this precedence. And then as well as we again print the n, this should be 3. This is how we manage the scope so that it doesn't change to 7 even if this expression has been evaluated inside the mangle function.
Yeah, I'm Amresh Vingamala. My contribution on this project is generating the bytecode of by parsing from the parse tree and the simple tables. Before we dive into the code about how we are generating the bytecode, I would like to give a brief overview on the mapping of the opcodes. So this is on the GitHub. This is the mapping of the opcodes. So for push it's 0, for pop it's 1, and for less than greater than it's 11, 12, and for basically for the branching it's 18, 19, and G stores and G loads are 25 and 26, which we'll see later on what exactly these opcodes and where they correspond to. This is the bytecode file. This bytecode, my bytecode part of the C program receives the parse tree and the symbol table, which are generated and explained by my teammate. While traversing, this generate bytecode is a function which recursively traverses through the tree and then pushes the opcodes into the vector, which will be passed on to the runtime environment, which will do the actual execution. So I would like to explain some basic nodes and then what exactly this function does. So this is the program node wherein the main head or the root of the tree goes in, and then the whole recursion happens on this. So this is the starting. The while is for all the statements inside the program node, and then exit is when after the whole recursion comes back. And let's dive into another node. Yeah, identifier is another node, which is one of the interesting parts on bytecode generation. So whenever I see an identifier node, I have to decide if I have to do a gstore or gload. Gstore is something like global, and then normal store is on the current context. So to find out if the identifier is in the current context or not, I have a function called find identifier, which recursively looks onto the symbol table map, and it checks whether it's on the current store, it's on the current symbol table, or it's in the recursive. And then if else if and else I mean the branching instructions were another challenging part on the bytecode. So what it does is exactly this is the main bytecode representation. What we do is whenever we see an if, we evaluate the condition. and then we evaluate the body, and then we do the else if. Else if is similar to the if block. If there's no else if, it's directly else, and then for the else it's a body. So it's the same on the bytecode representation as well. So generate bytecode recursively calls on the condition, then on the body, and then once it's done, I'll push a where am I? Yeah, I'll push the branch instruction. I'll put the branch that is the else if block or on the else block. So let's run a simple bytecode test for this program. It just runs the bytecode. It just takes an input and gives an bytecode. So if I run, it gives the bytecode, and this bytecode represents the opcodes. 047 is push 47, as because a equal to 47. 47 is a value and 0 is the opcode corresponding to the push. And then if you run this is just to let out the bytecode. And if you run on the directly on the malloc, if I run the same program from the malloc, this takes the if else output. This is for the compilation part, and .mallow gives it does the runtime, and it gives to. So it's the same program that I'm showing it on the bytecode and running on the runtime as well. Yeah, thank you.
Hi, I'm Ijaz, and I'm going to explain the runtime. Now, the runtime works based on a stack machine, and here we have a very simple statement, print 1 plus 2, and a very simple opcode for this statement. Let's see how the stack machine works. So IP is the instruction pointer, and SP the stack pointer. Right now we don't have anything in the stack pointer is at the bottom. So first we push 2, then we push 1, because we're going to add 1 plus 2. So we push 2 first, because what add does is it pops out the top 2 values in the stack, adds them up, and pushes it back into the stack. And what print does is it just takes the top value of the stack and prints it to the console, and then we exit. Now that we have a taste of the stack machine, let's move on to something a lot more interesting: function calls and recursion. So here's a simple function for a factorial. So we are calculating factorial of 3, and this is the bytecode for this function. Let's see how it works. So we have the instruction pointer, which basically points to a branch at the beginning, because we don't want to execute our function just yet. We want to go to the call. So we push 3 in, because that's what we are trying to calculate the factorial for. Now call takes in 2 values, which is the first instruction that we want to execute, which is the instruction of the function, that is 2, and then the number of arguments. So once you go into the function, a context is created based on the 3. So the 3 is stored at location 0 in context 1. So we go ahead, and push 1 is basically the first exit check that we do if 3 is less than 1, which it's not, so we branch a false to 13. And then this push 1 is for the subtract. So we do n into n minus 1, fact of n minus 1. That's what we do here. And we have subtracted it, and we have 2 now. So let's call factorial again, because that's how recursion works. So now we have called it again, and 21 and 30 are the return addresses, because we got a return once we hit our return. So now we have 2. 2 is still not less than 1. So we move on, and we subtract it, and on to the next call. So as you can see, contexts are getting created. So value of n in context 1 is 3. It's 2 here, and at context 3, it's 1. So now our exit condition is true. So now we return. As you can see, we are pointing at return now. And boom, recursion. So basically what it does is it takes out the top value of the stack, which we want to return, and then it takes out the next value, which would be the return instruction. And we come back to the return, which is 21 here. So now we do the actual multiplication. 2 into 1 is just 2. And then we return out of this context 2. And the return value is 2. And we multiply that with the current value in the context, which is 3. And we're back to the calling context, which we now have to print. And there you have it. That's the runtime. Let's quickly look at the code. The code is very simple. It's just a bunch of if conditions based on which opcode it is, and push condition is very simple. We push the next value in the code, which is the instructions, onto the stack. The rest of the opcodes work very similarly. Let's look at some example programs. So here I have a calculator program which has two values, A and B, and an operation 2. Operation 1 just adds it, operation 2 subtracts it. Let's run that quickly. Terminal. Okay, so now I'm going to compile my calculator and I'm gonna run it. So which is 2, 6 minus 4 is 2, and we are doing a subtraction operation. Let's look at another code, Fibonacci. So this is a very simple Fibonacci function. Right now I've written it to calculate the Fibonacci for 5. Let's do it for 7. And compiling Fibonacci and running Fibonacci and 13. That is the Fibonacci for 7. So there you have it. This is Marshmallow, a very simple program that we had loads of fun developing. Thank you.
Thanks.